Hi, I'm Andrea, and today I will talk about expansion of visual hints for improved generalization in stereo matching. This is a joint work with Yuxin, Niki, Arno, and Juho at Aalto University. So we all know that stereo matching methods are very good on the data where they are trained or similar distribution, but they can suffer on out-of-domain data, as we show here in this example on the tartan dataset. One way scientists found to overcome this is to use LiDAR guidance and obtain much better performance. But we may not always have available additional sensors. So we propose to use Visual Inertial Odometry to extract reliable disparity hints from the video sequence. The advantage is that we don't need additional sensors, while the disadvantage is that we obtain sparse and unevenly distributed hints, so we will have to do something about that. Our idea is to expand them and think about them as if they are in the 3D space. So we will connect them to obtain more guidance only if they are close enough in the real world. One way to do it is to expand them linearly. So we will divide the image in patches, and if there are points in the same vertical or horizontal line, we will connect them with a slanted line. And what we would obtain as a qualitative example is something like this. Another smarter way to do it is to treat them as if they are nodes of a graph, and then connect them with slanted planes if they are close enough in the 3D space. Bear in mind that 3D here is important because it allows us to connect only close points in the space. And with this technique, you obtain a much better connection between the points, and this is a qualitative example of it. In practice, we use our expansion for two different models. The first one is the well-known PSMNet. In this case, we pass the hints in the input, and we also add inside the model the ability to filter some of them, because visual odometry hints can be noisy in some cases, especially after expansion. These are qualitative results on the ETH dataset, and you can see that our method works a little bit better on the top row and also produces sharper estimation in the bottom row. Qualitatively, this turns out to improve results. Of course, we are not as good as LiDAR, but we obtain a very good improvement. The second model is the deep pruner, and in this case, we guide the patch matching stage. Instead of searching on the full range of possible disparity, we search in a neighborhood close to our guidance, and this proved to be very effective to remove artifacts and also to sharpen the details. Numerically, this is what you obtain in our ablation study. To conclude, I want to leave you with this slide summarizing the key takeaways from our work, and also on top a video of our method running at around 1 frame per second on an NVIDIA Jetson board embedded device. If you want further information, please read our paper and our poster.